Question number 1.8. Question number 1.8. A bar having a cross-sectional area A is equal to 700 mm square, is subjected to an axial load at the position indicated. The value of stress, we need to find out the value of stress in the segment QR. Value of stress is equal to load acting at QR by area of cross section. Now we need to find out load acting at QR. I am considering a section in between Q and R. Then sum of forces towards left or right of the section consider. I am considering towards left of section. Towards left of section, 63 kilonewton is tensile and 35 is compressive. Therefore, 63 minus 35, which is equal to 28 kilonewton, and the direction is direction of the higher magnitude, force with the higher magnitude. Here 63 is tensile, therefore 28 is tensile. Similarly, we can find out sum of forces towards right of section. If I am considering right of section, sum of forces 49 is tensile and 21 is compressive. Therefore, 49 minus 21, we get 28, and the direction is direction of force with the higher magnitude. 49 is tensile. Therefore, this is the segment QR, and at this side 28 kilonewton. This is also 28 kilonewton. Therefore, load acting is 28 kilonewton. Therefore, stress is equal to load by area. Load is equal to 28 kilonewton, 28 into 10 raised to 3, and area of cross section is 700. Solving this equation, we get 40 megapascal. 40 megapascal is the answer. Therefore, 40 megapascal. Option A is the correct. 40 megapascal. 40. Then 1.9. A 200 into 100 into 50 mm steel block is subjected to a hydrostatic pressure of 15 megapascal and pressure magnitude 15 megapascal. Young's modulus pressure given, so that is the stress value. Since it is hydrostatic pressure, that is volumetric stress, is equal to minus 15 megapascal. And Young's modulus and Poisson's ratio. Young's modulus E is equal to 200 gigapascal, which is equal to 200 into 10 raised to 3 Pascal, and Poisson's ratio is 0.3. Poisson's ratio mu is equal to 0.3. Then change in volume. We need to find out the change in volume, but Young's modulus and Poisson's ratio is given. But something related to change in volume is bulk modulus. So we need to write a relation between Young's modulus and bulk modulus. We have Young's modulus E is equal to 2K into 1 minus 2 mu. Then what is bulk modulus? Bulk modulus K is equal to volumetric stress by volumetric strain. Here the volumetric stress is given. Volumetric stress is equal to minus 15 megapascal. This is the hydrostatic stress condition. Stress acting at all the directions are same. 15 megapascal. So that magnitude of any one of the stress value is known as volumetric stress. Volumetric stress is equal to minus 15 megapascal. Then what we need to find out is the change in volume. Then volumetric strain is equal to change in volume by original volume. So we can write Young's modulus E is equal to 2 into volumetric stress by volumetric strain into 1 minus 2 mu. From this, volumetric strain is equal to 2 into volumetric stress by Young's modulus into 1 minus 2 mu. Volumetric strain is equal to change in volume by original volume. From this, change in volume is equal to original volume into 2 into volumetric stress into 1 minus 2 mu by Young's modulus. Here volume is equal to 200 into 100 into 200 into 100 into height 50. This is the volume. Then volumetric stress is minus 15 megapascal. Young's modulus is given 200 into 10 raised to 3 megapascal. 10 raised to 3 megapascal. All the values are given. Poisson's ratio is 0.3. We get change in volume is equal to about 90 mm square. Change in volume is equal to 90 mm square. Change in volume is equal to 90 mm square. That is the correct answer. 90 mm square. Then next question 1.10. A rod of length L and diameter D is subjected to a tensile load P. Which of the following is sufficient to calculate resulting change in diameter? We need to find out change in diameter by using Young's modulus only. We cannot find out change in diameter. By using shear modulus only, we cannot find out the change in volume. By using Poisson's ratio only, we cannot find out the change in diameter. By using both Young's modulus and shear modulus, we can find out the change in diameter. Both Young's modulus and shear modulus are required. Option D is the correct. Then link diagram question. A cylindrical container, radius is equal to 1 meter. Radius is equal to 1 meter. Radius is equal to 1 meter. And diameter is equal to 2 meter. The wall thickness is 1 mm. Thickness of wall is equal to 1 mm. Is filled with water up to a depth 2 meter and suspended along its upper rim. The density of water is given 1,000 kilogram per meter cube, and acceleration due to gravity G is also given. G is equal to 10 meter per second square. 10 meter per second square. The self weight of the cylinder is negligible. The formula of hoop stress in thin-walled cylinder can be used at all points along the height of the cylindrical container. These are the values given. Radius of this container is given, and thickness is 1 mm. Density of water is 1000 kilogram per meter cube, and acceleration due to gravity is given. This is the container. Water is filled up to 2 meter. Then axial and circumferential stress. We need to find out axial stress sigma A and circumferential stress or hoop stress. Hoop stress experienced by the cylinder at the mid depth. We need to find out axial stress and circumferential stress at the mid depth. And this is the container. This is the mid depth. At this point, we need to find out axial stress and circumferential stress. This is the direction of axial stress. But first, we are going to find out the axial stress. This is the point on which we need to find out axial stress. This is the 1 meter at a depth 1 meter. Sigma A. At this point, we need to find out axial stress. You need to find out axial stress. Here, this is a cylindrical container, and water pressure is acting at the bottom surface and at the curved surface, and the stresses are developed in this material to resist the force developed due to pressure of water. First, we find out axial stress. We can see the direction is axial direction, so we need to consider force along axial direction, and axial stresses are developed due to force acting at this bottom surface. Axial stresses are developed to resist the force due to pressure acting at the bottom surface. So what is the pressure acting at the bottom surface? P is equal to rho GH, because axial stresses are developed due to developed to resist the force due to pressure acting at the bottom surface. Rho is given 1000, G is given 10, and height is also given. The total height 2 meter. Height is equal to 2 meter. which is equal to pressure is equal to into 2 20,000 Newton per meter square. In megapascal, pressure is equal to this value into 10 raised to minus 6 megapascal. Therefore, pressure is equal to, we get 0.02 megapascal. Pressure is equal to 0.02 megapascal. Now we need to find out axial stress. The equation to find out axial stress is equal to PD by 40. P is given, and diameter is also given. Radius is 1 meter. Therefore, diameter is equal to 2 meter, which is equal to 2000 mm. Diameter is 2000 mm, and thickness is 1 mm. Thickness is equal to 1 mm. So solving this equation, we get axial stress is equal to 10 megapascal. Axial stress is equal to 10 megapascal. Then second part, we need to find out circumferential stress. Circumferential stresses are developed to resist the force due to pressure acting at this curved surface. This is the curved surface, and this is the pressure acting, and this is the pressure acting. And circumferential stress, the direction of circumferential stress is along the circumference, and the circumferential stresses are developed to resist the pressure or the force due to pressure acting at this circumference. Here the water pressure acting at the circumference is different, but we need to find out the circumferential stress at the midpoint. So we need to find out the pressure acting at the midsection, the circumferential, the force acting at this circumference. The pressure is equal to rho GH. Rho is 1000 into G is equal to 10, and height. Here the height is at midpoint. We are considering the pressure acting at the midpoint, not at the bottom, at the midpoint. So height is 1 meter. H is 1 meter. So we get 10,000 Newton per meter square. In megapascal, we get P is equal to 0.01 megapascal. 0.01 megapascal. Then equation to find out circumferential stress or hoop stress is equal to PD divided by 2T, and P is equal to 0.01 megapascal. Diameter is D is equal to 2000 mm. T is equal to 1 mm. Solving, we get 10 megapascal. So the answer is 10. Therefore option A is correct. Option A, 10 megapascal. Axial stress is 10 megapascal. Circumferential stress is also 10 megapascal. Then second question, if the Young's modulus and Poisson's ratio of the container, Young's modulus is given, Young's modulus is E is equal to 200 gigapascal, and Poisson's ratio mu is also given 0.3, then axial strain in the cylinder bar at the midpoint. We need to find out axial strain is equal to axial stress by Young's modulus minus mu into circumferential stress by Young's modulus. So we can write axial stress is 10 megapascal divided by 200 gigapascal, 200 into 10 raised to 3 megapascal, minus mu is equal to 0.3 into circumferential stress 10 by 200 into 10 raised to 3. Solving this equation, we get 7 into 10 raised to minus 5. 7 into 10 raised to minus 5. The answer is option C is the correct answer. 7 into 10 raised to minus 5. Then 1.13, the question number 1.13, a rod of length L having a uniform cross-sectional area A is subjected to a tensile force P as shown in figure below. The Young's modulus of the material varies linearly from E1 to E2 along the length of rod. Here, the Young's modulus of bar is not constant. It is varies linearly from this point to this point. The normal stress developed at this section SS. We need to find out the normal stress acting at this section SS. Then we have the stress acting is load by area. At equilibrium, stress acting is equal to load by area. In the equation of stress, there is no Young's modulus and Poisson's ratio. Therefore, stress is equal to load by area. Stress is independent of material property. If load and area of cross sections are given, stress is equal to load by area. This does not depend on any material property like Young's modulus, rigidity modulus, Poisson's ratio, etc. So the answer is option A, P by A. P by A is the answer. Then 1.14, a circular rod of length L and area of cross section A, length L, area of cross section A, and modulus of elasticity, Young's modulus is E, and coefficient of thermal expansion alpha is fixed alpha. One end of the rod is fixed, and other end is free. If the temperature of the rod is increased by delta T, change in temperature is delta T, then here the length of rod is L, area of cross section A, Young's modulus E, alpha, and coefficient of thermal expansion is alpha, and this is the rod, and one end is fixed and other end is free to expand. When the body is free to expand, the thermal stresses are zero, and thermal strain is equal to alpha delta T. This is the thermal strain. Option A, stress developing the rod is alpha delta T. That is wrong. There is stress is zero since the rod is free to expand. Both the stresses and strain developed in the rods are zero, but stress is zero, but strain is not zero. Stress developed in the rod is zero, that is correct, and strain developed in the rod is alpha delta T. Therefore, option C is the correct. Stress developed in the rod is zero, and the strain developed is alpha delta T. Option C is the correct answer. 1.15. The stress strain curve for a mild steel is shown in below. Choose the correct option referring to both figure and table. This is a figure given and this is the table given. So, what is P? P is a proportionality limit. P is proportionality limit. Q is elastic limit. And R is upper yield point. S is lower yield point. T is ultimate stress. And U is failure stress. P is equal to 3. P is 3. Q is 4. R is 1. S 5. And T 2. U 6. Option C is the correct. Answer. Option C. Then 1.6. Which one of the following type of stress strain relationship best describe the behavior of brittle material such as ceramics and thermostatic plastic? Here the material given is brittle material. Option A we cannot predict. It is if it is parallel to y-axis, it is rigid. If it is parallel to x-axis, it is ideal fluid. But we cannot identify whether it is x-axis or y-axis. Option B. Option B. Here, this is linear elastic followed by strain hardening. Option B is linear elastic followed by strain hardening. Option D is linear elastic, but option C is the correct. This is the brittle material. Brittle material, the deformation is very less, so stress will develop, but strain developed is 0. And at this point, the material failed. This line represents the failure of the material. So option C is the correct answer. In this case, option C is the correct answer. Then 1.17, a horizontal bar which a constant cross section is same is subjected to a loading as shown in the figure. The Young's modulus of AB and BC are 3E and E respectively. For the deflection at C to be 0, the ratio of P by F. So it is given that the deflection at a point F is 0. So the total deflection is 0. And this is bar number 1 and this is bar number 2. And the total deflection is 0. I need to find out, but we need to find out the ratio of P by F. We need to find out P by F. I am assuming in this case P is greater than F. We can take the reverse also. We can take F is greater than P. We can take that also. In this case, I am considering P is greater than F. Then total deflection, delta is equal to deflection of AB, that is delta 1, plus deflection of BC, that is delta 2. It is written that deflection at the point C is 0. Therefore, total deflection is 0. Total deflection is equal to 0. 0 is equal to delta 1 plus delta 2. From this we can write delta 1 is equal to minus delta 2. Delta 1 is equal to PL by AE. Delta 1 is P1. P1 is the load acting. L is same. Area of cross section is same. Young's modulus is 3. Deflection delta is equal to PL by AE. P is the load acting. Similarly, is equal to minus P2. P2 is the load acting at bar number 2 or bar BC, and L is same. A is same. Young's modulus is E. We can cancel A, E and L, and we need to find out P1 and P2. P1 is the load acting at section number 1 or bar number 1, and P2 is the load acting bar number 2. To get load acting at bar number 1, I am consider a section 1-1 here. This is section 1-1. Sum of forces towards left or right of section. I am considering sum of forces towards right of section. P is compressive and F is tensile. Here I am assuming magnitude of P is greater than F. So P minus F, which is also compressive, P minus F. Therefore P1 is P minus F. P minus F. Since it is compressive, we can give a minus symbol. So we can write L is cancelled, A is cancelled, P1. Instead of P1, we can write minus of P minus F. A is cancelled, E is cancelled by 3 is equal to P2. Load acting at bar number 2, consider a section in B2, in bar number 2, section 2-2, sum of forces towards left or right of section. I am considering sum of forces towards right. Only one force is acting, F, which is tensile. So P2 is F. P2 is equal to F. So we can write L is cancelled, A is cancelled, E is cancelled. P2 minus P2 is equal to F. So we can write negative can be cancelled. P minus F is equal to 3F. P is equal to 4F. Therefore, P by F is equal to 4. P by F is equal to 4. That is the correct answer. P by F is equal to, the ratio of P by F is equal to 4. 1.18. A circular metallic rod of length 250 mm, length of rod is 250 mm, is placed between two rigid immovable walls as shown in figure. The rod is in perfect contact with the wall on the left side, and there is a gap of 0.2 mm between the rod and the wall on the right side. If the temperature of the rod increased by 200 degrees Celsius, so change in temperature is equal to 200 degrees Celsius. 200 degrees Celsius. The axial stress developed in the rod. We need to find out axial stress developed in the rod. The Young's modulus of the material of the rod is, Young's modulus is given, Young's modulus is equal to 200 gigapascal, 200 into 10 raised to 3 megapascal, 10 raised to 3 megapascal. And the coefficient of thermal expansion, alpha is also given, alpha is equal to 10 raised to minus 5 per degree Celsius. These are the given values. Length is given, length is equal to 250 mm. We need to find out thermal stresses. Thermal stresses are developed only when the expansion is prevented. Here we can see that left hand side is fixed, but there is a gap in between rod and support at the right hand side. So when the rod is expand up to 0.2 mm, there is no stresses. If the rod is expand beyond the 0.2 mm, then only the stress develop. So first we need to find out the expansion of rod. Expansion of rod is equal to expansion of rod delta L is equal to alpha L delta T. Here alpha is given 10 into 10 raised to minus 5, and length is 250 into change in temperature is 200, change in temperature 200 degrees Celsius, 200. And solving this equation, change in length, we get 0.5 mm. So the expansion of rod is more than the gap, so some stresses are developed. But during the first expansion, when this rod is expand up to 0.2, the stress developed is 0. So stresses are developed only due to the expansion prevented. Here the expansion prevented is equal to free expansion. This is the free expansion 0.5. It's the free expansion minus this gap. This is the expansion prevented. Stresses are developed only due to this expansion prevented, which is equal to PL by AE, and P by A is the stress developed. So expansion prevented, free expansion is 0.5 and the gap is 0.2 is equal to stress into length is 250 by Young's modulus. Young's modulus is 200 into 10 raised to 3 megapascal. 200 into 10 raised to 3. Solving this equation, we get sigma is equal to about 250 megapascal. Sigma is equal to 240 megapascal. Sigma is equal to, solving this equation, we get sigma is equal to 240 megapascal. 240 megapascal. Therefore, the answer is 240 megapascal. Stresses are developed only due to the expansion prevented. Here the free expansion delta 5. Free expansion means if the support is not there, it is expanded up to 0.5 mm. But expansion is prevented, but only 0.3 expansion is prevented, since there is a gap of 0.2. Therefore, expansion prevented is only 0.3, and stresses are developed only due to this expansion prevented, and the stress is 240 megapascal.